Hello all, I'm back for some more of Chapter 6 and what I think is probably one of the most important notes of the year. It's important because it allows us as chemists to decide how much reactant we need to add to our system in order to get a certain amount of product. And again, if I think about what we do as a chemist, the goal as a chemist might be to make so many grams of this chemical. Maybe it's for the food industry, maybe it's for a medical industry, but the goal is we have a company and we make, in this case, the chemical is called chloroform. Chloroform is what we use for surgery to put patients under. So, if I look at question 3 on page 214, I'm just going to use this as an example because it allows us to figure out really what is the purpose of doing chemistry, right? Why do we do chemistry? And the whole idea is, one, to understand the world, but number two, to make stuff. All right, so in question 3, we've got a chemical called carbon tetrahydride, CH4, reacting with chlorine gas. And we're going to make the chemical that we're trying to make, which is, called chloroform, plus 3 hydrogen chlorides. Now, notice what's happening here is that there are 4 hydrogens on carbon here, and there's only 1 hydrogen left on carbon here. So 3 of these hydrogens have to come off. What they're going to do is they're going to undergo a displacement reaction with the Cl2. So the Cl2 is ClCl. What's going to happen is one of the H's will come off, kick a Cl off, and the Cl will jump onto where it replaced the H. Then a second H is going to come off to the second Cl2 and kick off a Cl2, and the Cl will join, the second Cl will join here, and then the third H will come off here and kick off another Cl, and the Cl will join. So I'll end up with carbon and hydrogen and 3 chlorines. And in each case, each of the hydrogens kicked off a Cl from a Cl2 to make HCl. So there's our chemical. And again, maybe our company is in the business of making this chemical here, which is chloroform. Now notice that what we've been talking about are mole ratios. And the mole ratios are based upon the coefficients in our balanced equation. The coefficients are 1 CH4 reacting with 3 Cl2s to make 1 CHCl3 and 3 HCls, right? Directly from our balanced equation. 1 plus 3 makes 1 plus 3. Okay, so there's again why we're balancing our chemical equations. Now the question says 25.8 moles of chlorine is going to react, and how much chloroform am I going to make? Okay, so the question is telling me that I'm going to start with 25.8 moles of chlorine. Boy, this stylus is not working tonight. 25.8 moles of chlorine, and the question is, how many moles of chloroform can I make? Now we're going to use mole ratios like we've been using all along here, and the mole ratios are basically going to allow us to say, if I know that every time 3 moles of Cl2 disappears, 1 mole of chloroform is going to be produced. Okay, so in order to find my number of moles of chloroform, switch my stylus. I need to know the number of moles of chlorine, and then I'm going to multiply it by my mole ratio. So the mole ratio, again, remember what I'm trying to do here is I'm trying to look at 2 compounds in my equation up top here. So if I look at my equation up top, here's my original equation, and what I'm trying to do is I'm trying to calculate CHCl3, right? And there's 1 CHCl3. So I'm going to put 1 mole of CH. Oh, I didn't leave myself enough room there. Cl3, and I'm trying to get rid of the moles of chlorine. So I can see that when 1 mole of this is made, 3 moles of chlorine were used. So I'm going to put 3 moles of chlorine. So notice that all of this here, right, came from the balanced equation. And then this part here and here is what the question is asking. So I've got 2 parts to this equation. One is my unknown, which is the number of moles of chloroform, right, which is right here, number of moles of chloroform. My given is the number of moles of chlorine gas. Sorry, it was 25, yeah, 0.8 moles. Number of moles of chlorine gas, and then the 1 and the 3 have come directly from my balanced equation. So let's put the numbers in here now for what we have. Let's get rid of some of this stuff. Okay, so my number of moles of CHCl3 that I'm going to make is equal to the number of moles of chlorine, which is 25.8 moles of chlorine, times I have 1 CHCl3 divided by 3 chlorines. Okay, again, right from my balanced equation at the top that's off the screen right now, right from here, right, 1 mole of CHCl3 comes from 3 moles of chlorine, right? So that's where this whole piece comes from. Now, if I look, I can take my moles of chlorine on the top and chlorine on the bottom, and I'm left with 25.8 moles times 1 divided by 3. And notice that what I'm left with is 1 chloroform, right, divided by 3. And the chlorine is all gone. So what I end up with now is 25.8 times 1 over 3, which equals 8.6 moles of chloroform. All right, so what I've done is I've taken my balanced equation to come up with a mole ratio, right? My mole ratio comes from here. I've taken the numbers of moles from the question and my unknown number of moles from the question, and I've created a relationship between them so that the number of moles of chlorine of chloroform here, which is my unknown, right, there's my unknown, is equal to my known number of moles, which is the chlorine gas, times the 1 over 3, which is the mole ratio from the question. Let's try this again with the second part. There's a B part of this question. So let's write out my equation again. I have CH4 plus CH plus 3 Cl2s makes a CHCl3 plus 3 HCls. Right. Now, in the second part of this question, it says, if 1.88 moles of chloroform is produced, how much chlorine did I need? So, I'm told that I'm going to make 1.88 moles of chloroform, and the question is, how many moles of chlorine did I use? Okay, so I'm going to do the same thing I did before. I'm going to look at my balanced equation, and I'm going to look at what my known is and my unknown. I know that my number of moles of chlorine, which is my unknown here, right, number of moles of chlorine is unknown, is equal to my number of moles of the known, which is chloroform here, times the ratio. The ratio has to have the chloroform on top and the chlorine on top and the chloroform on the bottom, because I need to get rid of the chloroform and keep the chlorines. So the mole ratio, and from the balanced equation, says I have 3 moles of chlorine in my balanced equation, right there, and I have 1 mole of chloroform right here. Okay, and notice that my chloroform here and my chloroform here disappear, and I'm going to take my number of moles of chloroform, which was given in the question, 1.88, times 3 over 1, and I'm going to get moles of chlorine gas left over. So 1.88 moles of chloroform times my 3 to 1 ratio is equal to 5.64 moles. So what that's telling me is that if I want to make 1.88 moles of chloroform, I need to use 5.64 moles of chlorine. Now notice there's an important question that I'm ignoring here intentionally. Second question, that question is, what about the other reactants? We don't know how much of this is here. We don't know anything about this one. So how can I look at the reaction if I only know about one reactant? And the answer is, if I look back at the question says, if 25.8 moles of chlorine react completely with sufficient methane, right? What that's telling me is I've got more than I need of this. This is what we call an excess chemical. Excess means there's more than I need, right? If I wanted to make a sandwich for my lunch tomorrow and I went to the store, and let's say I was going to make a ham sandwich. I went to the deli and I said, can I have 2 slices of ham to make a sandwich? And they shaved me 2 slices of ham. And then I went to the bakery aisle and I thought, oh, I got to buy a loaf of bread. Right? So when I'm done, let's assume I require 2 slices of cold cuts for my sandwich, and I have 2, so I'm going to make 1 sandwich. But what I'm going to have left over is almost an entire loaf of bread. There was excess bread, right? The thing that decides how much of a sandwich I can make is the one that runs out first, which in this case is my cold cuts. I only have enough cold cuts for 1 sandwich, and after that, all that bread is left over. The same thing here. It's telling me that I have more of this than I need, so that what decides how much product I'm going to make is the one that's going to run out. So when you see the word sufficient, right, that tells me there's enough of that. Or if it says that this one is limiting, those are the 2 words that we see, sufficient and limiting. Limiting means it's the one that's going to decide. It's going to limit how many sandwiches I can make, how much product I can make here. Right? Excess has nothing to do with it. Right? Again, notice I'm not talking about this, and I'm not talking about this. Because at the end of the day, I really don't care. So long as I've got enough of this to make my products, that's good enough for me. Right? What I care about here is the reactant and the product that are in the question. So I'm going to ignore the 2 other components in that chemical equation. All right, so that being said, that's the homework from 6.3 from last night. I want to go back and look at our note now for 6.4. And 6.4 is called stoichiometry. We talked about stoichiometry before. Stoichiometry is how we use math and mole ratios to decide either how much reactant I need or how much product I can make. Okay, so stoichiometry is using math to decide the quantity of reactants or products in a chemical reaction. Now, in a lot of cases, we'll be asked not for the number of moles, but we'll actually be given grams. So in the last question that I just did a moment ago, this one's telling me that to make 1.88 moles of chloroform, I need 5.64 moles of chlorine. Right? But the question is, how do I know how much is 5.64 moles of chlorine? So today we're going to do the last big step in this whole process, which is to decide what mass I need of my reactant in order to make product, or what mass of product I'm going to get when I have a certain amount of reactant. So I'm going to follow 4 steps here. Okay, number 1 is I'm going to balance my equation. Okay. Number 2 is I'm going to be told how many grams of either reactant or product are given. So once I know the number of grams, I have to calculate the number of moles. Right? So I'm going to calculate little n. Once I know little n, I'm going to use ratios, mole ratios, to determine the moles of unknown. And then once I know how many moles of unknown, I'm going to calculate the mass. All right? So let's look at this question here. Okay, so the first sample says if copper reacts with silver nitrate, I get copper nitrate and silver. Okay, so here's the question. When copper reacts with silver nitrate in solution, AgNO3, solid silver and a blue solution of copper nitrate is formed. The balanced equation is this. Now the question says if 1.43 grams of copper are reacted, what mass of silver am I going to get? So notice in my question that I have a mass of copper and I'm looking for a mass of silver. Okay, let's go to our problem. Let's go to our whiteboard here. Whoops. Our whiteboard. Okay, so this is the sample from page 216 in the textbook. Now, recognize this is a big question, right? Once you get your head around it, you'll think, wow, that is really easy. But it takes some getting used to, right? It really takes doing a few of these to get your head around it. So sample number 2 says, I'm reacting copper with silver nitrate, and I'm going to make copper nitrate. It's copper 2 nitrate, actually, and pure silver. Right? And to make this work, I have to balance my equation. I have 1 copper on the left, 1 on the right. I had 1 silver on the left and 1 silver on the right, and 1 nitrate on the left, and 2 on the right. So I put a 2 in front of my silver nitrate here, and then I've got to balance my silvers over here. So it's now balanced. Now, the way that you're going to do this question, notice that I've used my entire width of my screen here on my device, and I'm going to basically use the whole screen as my working space. So what I'm trying to do here is I'm given a mass of copper. Come on, out of here. I'm given a mass of copper. So I'm writing under copper. So make sure you go all the way across your page. 1.43 grams. Right? That's my mass of copper. Again, notice I'm going to try and stay right under the Cu there. And what I'm trying to calculate is how many grams of silver am I going to get. Now, I can't say that 1 gram of copper makes 2 grams of silver. It doesn't work that way. Right? What I know, because the masses of copper and silver are different, all I know is 1 mole of copper makes 2 moles of silver. So I've got to convert mass to moles. So I know how to do that from my last test. Right? To do that, I'm going to say the number of moles is equal to the mass divided by the molar mass. The mass is 1.43 grams, and my molar mass for copper is 63.55. So my number of moles here is 0.0225 moles. Okay, so I now know the number of moles of copper. What I also know is I can use the number of moles of copper to determine the number of moles of silver. Okay, we just did that in 6.3. So I'm building and building and building. So we're using the skills that we just used in 6.3. If you haven't got 6.3 under your hat already, go back and revisit it. Okay, so what I know is my unknown here is the number of moles of silver. So my number of moles of silver is unknown, right? I can see that over here, number of moles of silver. And it's equal to the number of moles of copper, which is my known. I know how many moles of copper there are, 0.0255, times my mole ratio. My mole ratio says I always get 2 silvers for every 1 copper. Right? 2 silvers for every 1 copper. So I'm going to take my numbers here. Number of moles of copper was 0.225, sorry, times 2 over 1, and I'm getting 0.0450 moles. Okay, 0.0450 moles. So that's my number of moles of silver, which is this number here. Okay. Now I know my number of moles of silver. I can calculate the mass of silver because I know that the mass, which is unknown, is equal to my number of moles times the molar mass. So, if I can move this over or not. Oh, don't have room. So my number of moles is 0.0450. Actually, I'm going to get rid of this arrow because it's just in the way. Mass equals number of moles times molar mass. Again, notice that I'm trying to work down under the silver here for all of my silver calculations. My number of moles is 0.0450 moles. Times the molar mass for silver. Now, notice this is 2 silvers up here, right? I want the molar mass. The mass of 1 mole of silver on my periodic table is 107.87. I haven't got room to write this. I've run out of space on my screen. Whoops. Oh, darn it. 107.87. And I'm going to get a final answer, which is 4.85 grams. Okay, so if we go back up the page here a little bit, we'll see that we started with our copper and silver in our reaction. We started with a known mass of copper and an unknown mass of silver. Right, so remember my first step, step 1, balance my equation. Step 2 said calculate the mass of your known to moles. So I did that here. Right, I determined based on my number of moles how many up here, my number of grams up here, I used it to calculate my number of moles. Step 2. Step 3, use the mole ratio to find the number of moles over here. And then step 4, use the molar mass to calculate your unknown mass, which is what the whole question was about in the first place. Now be careful not to use 2 silvers for your molar mass. Right? That would be 2 moles. I want the mass of 1 mole, which is what the periodic table tells me is 107.87. Okay, I'm going to move on. I want to do another sample. I'm going to do 2 more samples, and then that will be it. We're going to have a live class on Tuesday, the day after tomorrow, this week, and hopefully we'll go over some of this stuff together. I'll put some samples together. We'll do some. If you've got questions, I'll be happy to do them. was a sample in our textbook on page 217. And it says, when powdered iron oxide and powdered aluminum are mixed and they ignite, a spectacular reaction occurs called thermite. The temperature is so high that it melts the iron into liquid iron. Okay, so it says railway workers carrying out a repair on a locomotive axle frame using the thermite reaction. So again, the axle is made out of steel, basically iron. And what I need to do is the axle is broken and I want to weld it back together. So I'm going to mix some of the iron oxide with the aluminum and I'm going to make my product, which is iron. So here's the reaction. Fe2O3 is going to react with solid powdered aluminum. And what I'm going to get is aluminum oxide and iron. Now, it tells me in the textbook that this is solid, this is solid, this is solid, and this is a liquid. It's liquid steel. As soon as it cools down, it's going to solidify into solid iron. So, question says, the worker needs to produce 50 grams of liquid iron to fix the weld. This is what I need, 50 grams of iron. Okay, so here you are at the site, got a broken axle, and the question is, I need 50 grams to fix this problem. How much iron oxide should I get out of my container? Right, so again, notice my mass of iron oxide is here, my mass of iron is here. My known is here, my unknown is here. So I'm going to basically follow the same steps. I'm going to use M to calculate the number of moles, use this number of moles to calculate the number of moles on this side using mole ratios, and then I'm going to use the molar mass to calculate my unknown mass, or how much iron oxide powder do I need. Okay, so let's scroll up just a little bit. So to calculate the number of moles here, it's going to be mass divided by molar mass, just like we did on our test. 50 grams divided by the molar mass for iron, which is 55.85 grams per mole. And I'm going to get 0.895 moles. Okay, now I'm going to use that number, right? I'm going to use this number N to calculate this N by using the mole ratios. So I'm trying to calculate number of moles of iron oxide, right? The number of moles of this chemical. So there's my unknown right now. So notice I've already done one calculation down here. Okay, now I'm going to do my second calculation. To calculate my number of moles of iron oxide, it's going to be equal to the number of moles of iron times my mole ratio. I have 1 mole of Fe2O3 every time there are 2 moles of iron, right? 1 mole of Fe2O3 and 2 moles of iron. Notice I put the iron down here in the denominator because I want it to cancel with the iron up here, and I want to be left with moles of Fe2O3. So let's put our numbers in. Number of moles of iron is 0.895. Times 1 over 2. 0.450 moles. Okay, so you started here, I calculated this number. Then I use this number to calculate this number moles. Now I'm going to use this number to calculate this number. Right, so now my goal is to determine the mass of Fe2O3. Okay, so my mass is equal to the number of moles times the molar mass. Number of moles is 0.450, but I don't know my molar mass yet. The molar mass here is the molar mass for Fe2. Oops, I should leave myself more room. This is molar mass for Fe2O3, which is 2 times 55.8 plus 3 oxygens, 16.00. So I'm getting a molar mass for iron oxide, which is 159.7 grams per mole. Again, all from our last test, right? Molar mass, capital M. So now I'm going to go use this number. Oops, I'm going to use this number here as big M in this equation here, so I can calculate my little m. So 0.45 moles times 159.7, and I'm going to get 71.5 grams. Okay, so started with my mass over here, calculate a little n using mass over molar mass, calculate a little n here using my mole ratios, calculated my mass here using the molar mass again, and it says if I need 50 grams of liquid iron, I better start with 71.5 grams of Fe2O3. 71.5 grams of Fe2O3. Okay, I think that's it for me. I'm going to stop there. I'm going to leave you with the last questions, and there's a bunch of them here, on page 218. Oops. So we've done this problem here with the copper and silver. We've done this problem here, which is the thermite reaction, making liquid iron out of Fe2O3. And I'm going to leave you for today with these questions here on page 218. Now, my suggestion to you is to work through the 2 samples that I just did, and then slowly work your way through these questions again. If you're struggling with this, go back to the work from yesterday for 6.3 and look at the sample again here on page 214, and then look at those 3 questions down here again that we just did for homework last night. Again, really stay on top of your homework. If you get behind with the homework even one single day, it can be really catastrophic. So really try and stay on top of your homework, and you'll be in good shape. So that's it for today, Monday. I will hopefully connect with as many of you as are able on Tuesday, and we will take up some of this work. And I think Wednesday I won't plan anything new either. Wednesday I might just give you a work period to continue working on some more questions, which will be the other part of those questions on page 219 here. But we're not going to do those today, right? For today, let's just worry about those 8 questions on page 218. They will take a while to do. By the time you've done those 8, you'll be a pro at doing these. So it may look really brutal. It's actually not bad once you've done a few of them, because it's always the same, right? So steps, 1, balance your equation. 2, calculate little n for your known. Step 3, calculate little n for your unknown using stoichiometry. Step 4, calculate your mass using your molar mass. Right, same 4 steps every time. Okay, hope everything's well. If you're struggling or need